Hello, I'm Yaroslav Blanter. Today is March 13. I'm going to give the fairy tale 17 about the rainbow. Now this is the setting which we are going to use. The tale is also uploaded on Brightspace, and this picture in particular and the quality on Brightspace is better, but I will start with this one anyway. So let me first start with the facts which we are going to explain today. That's the basic facts about the rainbow. Now, one thing is that we see a rainbow as a semicircle, and we see a rainbow only if the sun is behind us. So we are standing between the sun and the rainbow. So the semicircle comes in colors, and colors are red on top and violet on the bottom. And we only see it if the sun is over the horizon. The angle at which the sun is over the horizon is not more than approximately 42 degrees. So those are two things which we are going to explain. One is this angle, 42 degrees, and another thing is the order of colors. That we will do in the first part of the lecture. Now, the third fact which we need, this is called primary rainbow. That you have seen a lot of times. You probably have also seen a secondary rainbow. So that's a rainbow which appears on top of the primary. So that's the secondary rainbow. And it has the reverse order of colors. So it has violet on top and red on bottom. And today we are not going to talk about the secondary rainbow. That's a part of the homework. So if you want to do the homework related to this tale, this homework would be about the secondary rainbow. Now in the second part of the lecture, we will be talking about something else, which you probably have never seen or maybe once. Now below this primary rainbow, we also have a set of so-called supernumerary bows. And the supernumerary bows also have the same order of colors as the primary rainbow. So that's always red on top and violet on the bottom, always like that. And so in the second part of the lecture, we will explain supernumerary bows. I can only use a blackboard up to here, so I don't have much space. I need to keep this picture at least for the first part. So I will be quick. I will be often erasing things I have just written, but since we are recording them, it should be fine. Now, this first part, okay, so the first persons who seriously looked at the rainbow was Descartes. So the same Descartes as, for instance, introduced the Cartesian coordinates which we use today. So we will be first talking about his concept of his theory of the rainbow. Now there is some story associated with that. It was published in 1637. And you know, Descartes was French, but he had some differences of opinion with the Catholic Church, so he had to flee France, and he spent a lot of time, I think over 20 years in the Netherlands, in different places. I think he was for some time in Leiden, for some time in Utrecht, sometime I think in Breda, I'm not sure. And this is what he published. He published a book on optics in 1637, and this rainbow is part of this book on optics. But then people said that some things which he published were actually not found by him, but were found by Snellius. And Snellius died in 1626, so before Descartes published that. And that's okay, that's still a question which has not been resolved, because obviously we don't know whether Descartes plagiarized anything from Snellius or not. And if you have studied in the Dutch school, then the refraction law is called probably Wet van Snellius. And if any of you studied in France, the refraction law is called the law at Descartes. So that's obviously an issue which has never been resolved and probably will never be resolved. But anyway, so now let's go to physics. So the idea of Descartes was that the rainbow comes from the refraction of light. And this is what this picture shows here. Now we need rain to see the rainbow, and if we have rain, we have water droplets in the air. And this picture shows one water droplet. And here the ray is coming from the left. Now we have, I will denote R, the radius of the sphere. Let me put it here, capital R. And this ray of light would be parallel to the Earth at this distance rho from the center of the droplet. And so then it goes here it gets refracted, and then that's why it doesn't go straight. It goes under some angle. At this point it gets reflected from the surface of the droplet. It goes here, and here it gets out. Now the total angle at which it gets out is, I call it gamma, so that the angle between the direction of this ray, which was doubly refracted, so it's double refraction, and the horizontal line, which is horizontal because it's parallel to the surface of the Earth. So this angle gamma is exactly the angle at which the sun is over the horizon. So when we say the rainbow is at not higher than 42 degrees, it means that this angle gamma is not higher than 42 degrees. This is what Descartes calculated using basically high school geometry. And that's what we are going to do in the first part. Now we need some notations for that. I will call this angle alpha, and I will call this refraction angle beta. And this x, which is that's a dimensionless parameter, which is this distance rho divided by the radius of the droplet, I will call it the target parameter. And what we are going to do first is to calculate this function gamma, this angle gamma, as the function of the target parameter x. Now there are two things which we need for that. One thing is we need the refraction law. And the refraction law tells you that, let's see, that sine alpha is n sine beta, with n being the refraction index. And for water, n equals to 4/3 approximately. Well, let me put it approximate. N is approximately 4/3. Right. That's one relation. We related alpha and beta. Now we also need to relate them to gamma. Now try to follow me. I'm now considering a triangle A, B, O. So I'm considering a triangle A, B, O. And we know that the sum of the three angles of a triangle is pi. As for every triangle, the sum of three angles is always pi. Let's see, this angle, we know this angle is alpha, because this angle is the same as this one, because this is one line, sorry, no, it's not alpha. No, I'm sorry. It's not alpha. No, I think I need another triangle. Let me call this B prime, and I need triangle A, B prime, O. A, B prime, O. And then this angle is alpha, because this is one line and this is one line, so this angle equals to this angle. So I'm now starting to calculate the sum of these angles, and one of the angles is alpha. Now what is this angle? This angle is, if we consider this triangle, now ABO, then this angle is beta, and this length is equal to that length, which is, both of them are the radius of the sphere, which means that this angle is also beta. Okay, we actually called it beta. So those two angles are both beta. And this means that this angle is pi minus 2 beta. So we have this one, which is pi minus 2 beta. Now this angle is a half of this angle. But this angle is gamma, because this is horizontal, so this is parallel to that. And this line, yeah, it's not a very good drawing, but this line continues here. So this is an angle between this line and this line is the same between this line and this line. So this is half of that, so this is gamma over 2. And that should be equal to pi. Now I see that pi cancels, and I get gamma equals to 4 beta minus alpha. Let me check that with my notes. Minus 2 alpha, yes, minus 2 alpha. Okay, now that's another relation. Now I also need to relate this to x, and I can easily relate this to x, because now if I look here, this is rho, and this is r, and this is alpha, which means I have rho equals to r sine alpha, and that means that sine alpha is rho divided by r, which is x. And from here we get the sine of beta. So I can write alpha as arc sine of x. And sine of beta is then 1 over n sine of is x over n, because it's 1 over n sine of alpha. And then beta is arc sine of x divided by n. Okay, now I just need to collect all of that and write gamma. So let me formally write it as 4 times arc sine of x over n, minus 2 arc sine of x. So we have done the first part. We have calculated this angle gamma as the function of x. Now let's see how it behaves. And for that we need to find the maximum. Now I'm going to, I think I'm going to erase all of that. So d gamma over dx. The derivative of the arc sine is 1 over square root of 1 minus x squared. So I get minus 2 1 minus x squared from here. And from here I get plus 4 divided by n, 1 over square root of 1 minus x over n squared, which is 2 1 minus x squared minus 4 plus 4, sorry, minus 2 plus 4 n squared minus x squared, unless I forgot something. And if I'm looking for a maximum, this must be 0. And now I can, for instance, divide this by 2, n squared, and then I get 1 over minus x squared equals to 4 n squared minus x squared. Right? And this gives me n squared minus x squared equals to 4 minus 4 x squared, which is x squared. Let's see, here I get 3, so it's 4 minus n squared divided by 3. So x at the maximum, so let's call it, let's see, again, I want to be consistent with my notations. I will call it x naught. That's square root of 4 minus n squared divided by 3. Let me check with my notes. Yes, that's exactly what I get. And if you now put here n equal to 4/3 corresponding to water, then you approximately get this 42 degrees. So that explains the 42 degree observation, and that's what Descartes did. Now you can also easily explain the order of colors, because n is not exactly 4/3. N actually depends on the color, and for red and violet it would be slightly different. And then if you take it into account, you will see that the positions of the maximum for red and violet are slightly different, and that's why you see red on the top and violet on the bottom. So that's all fine. Now we can do a little bit more than Descartes did, so let me erase this. We can also estimate the intensity. Now for the intensity, we take into account that, okay, here we have talked about just one ray, which is coming at this target distance rho, but in fact there are many rays coming at all possible rhos and also at all possible angles, at all possible positions outside the board. So if you want to estimate the intensity, it should be proportional to d of rho squared, because now we are talking about two dimensions. We have 2 degrees of freedom perpendicular to the board, and this is 2 rho d rho. Now instead of rho I want to write gamma, so I will write 2 d rho d gamma d gamma. And of course d rho over d gamma is just d gamma over d rho to the power minus 1. And we know that or we can also write x if you want. It would be also proportional to d gamma over dx. And we see that because at x equals x0, at x0, gamma has a maximum, so this derivative is 0. The intensity has a singularity. The intensity at this point diverges. And if we start drawing this primary rainbow, according to Descartes, let's maybe not draw everything. Let's only take one color to make things easier. We see that the intensity here is 0. So here there is absolutely dark, everything, and the intensity here, if I try to write it, to draw it as a function of gamma, so we are now talking about how it goes down. So for gamma equal this gamma naught, so this 42 degrees. The intensity here is 0, here it has a singularity, and here it goes down, and you can actually calculate how it goes down. Right. Now that's not exactly the picture which we started from. First of all, here we also have somewhere we have a secondary bow, but that's not a part of this lecture. That's a part of your homework. Now we suspect that this is not completely dark, so the intensity is not completely 0. And also we know that below we have supernumerary bows. But in the Descartes rainbow, the intensity just goes down smoothly. So for supernumerary bows, we would like to see some oscillations. And in the picture of Descartes, we don't have any oscillations. And to explain them, we need to go to the second part, which is airy rainbow. I will take another piece of chalk and we'll come back to the screen in a second. Yes, so we are going to look at airy rainbow. This I'm going to erase. Now, for Airy, I don't have the year when he published that, but Airy, George Biddle Airy, was also an interesting character. he was, well, British. He had a title of the Royal Astronomer, and as a royal astronomer, in particular, his task was to establish the Greenwich Observatory and to demarcate, to designate the zero meridian. So the zero, what is it, longitude meridian. But well, he was also doing research, and that was his probably most important piece of research, and then we will see why in the end. Airy realized that the supernumerary bows, which we couldn't explain with the simple picture, are due to interference. And for the interference, you cannot just consider one ray, you need to take two rays and see what they are doing. And that's what we are going to do. I will consider two rays. And what we need to do in the end, we need to calculate the length, light, the length of the path of the light. So to keep all rays, to count it in the same way, I will be counting from this plane, and I will be counting up to, let's see, up to this plane, because of course rays come at different target distances, and then the distance here is different. So we need to set the starting point in the same way. Now another complication is that actually what I need is not the distance. What I need is the distance multiplied with the refraction index. I believe it's called optical path, but I'm not sure. Now, so and part of this distance, light comes through the vacuum with the refraction index 1, and another part of the distance, light comes in water with the refraction index n. So what I will be calculating is not really the distance, even though I will call it distance. I will be calculating this optical length. So the distance multiplied with the corresponding refraction index. Okay, so let's first calculate it. So let's take a ray with some target parameter x and calculate this distance L of x. Now, first of all, I see that this distance from here to here plus from here to here is the same as distance from here to here plus this one. So it's enough for me if I calculate this, add this, and multiply by 2. Let's see. So let's first calculate this and multiply by 2. This is the same as that. And this is the radius of the sphere minus this. And this is r sine alpha. So what I get for this first part is 2r 1 minus sine alpha. No, sorry, it's not sine, it's cosine. I'm sorry. Okay, now for this one. For example, I can take, I mean, again, that's a triangle with equal sides. I can put a line in the middle, and then this distance would be r times cosine beta. and the total would be 2 times r times cosine beta. And yes, and I need to multiply it by 2 because I'm multiplying everything by 2 and with m. Because this part is inside water, and if it's inside water, then we have the diffraction index, which is not 1. Okay, great. Now we can actually, we can rewrite it in terms of x, because we know that this is, okay, so we know that sine alpha is x, which means cosine alpha 1 minus x squared. And we know that sine beta is x over n. So cosine beta is square root of 1 minus x squared over n squared. So I can just write it as 2r 1 minus square root of 1 minus x squared plus 4r n times the square root, which will give me n squared minus x squared. And now I can actually take the, I can see where this L has a minimum. And I will not do it, it's an elementary calculation, but I only remark that the point of minima of L is exactly this x naught, which we found in the previous part. So if you take a derivative of this function, it would be and put it to 0, you get the same equation as you got in the previous part, and then x naught would be the position of the minimum. Sorry, I have to erase parts of that again. Okay, good. Now I said we need to take 2 rays. Let's see. What I want to calculate is I want to be close to this minimum, because I'm interested in being close to this critical angle. And I want to take 2 rays, one going with x naught plus some delta x and another one with x naught minus delta x. And I can just calculate what is it. So I can Taylor expand this in powers of delta x. So what I have is, in the first, okay, now maybe I should do it separately. Let me just expand. So L of x naught plus delta x is L of x naught plus delta x times L prime of x naught. This is 0, because at x naught L has a minimum, plus 1/2 delta x squared, second derivative of x naught. And we will also need the next term, which is 1 over 6 delta x cubed L third derivative over x naught. And now I see, if I take this difference, these first order terms cancel anyway. 0 order terms cancel because they are the same. Second order terms are the same. So what I get is 1/3 delta x cubed, and then the third derivative at x naught. Let me make it consistent with my notations. No, I cannot make it consistent with my notations, never mind. But what I want to do, I think I don't need that anymore. I will now erase it. What I want to do is I want to use not delta x, but I want to use delta gamma. Because in the end of the day, I want to express all quantities in terms of the angle gamma. And we know that gamma itself has a maximum at x equals 0, so I can also expand gamma of x naught plus delta x, which I will just call gamma. That would be gamma of x naught, which I will call gamma naught. And I have the first derivative, so gamma prime of x naught delta x, and we know that this is 0, because gamma has a maximum. And then I need the next term, which is 1/2 gamma double prime of x naught delta x squared. But I know it's a maximum, so I know that the second derivative is negative. And let me just take it up front into account. I will just write the absolute value and put here minus. And then I can relate my delta x, so I get delta x squared is let's see, is gamma naught minus gamma, which is a positive quantity, times 2 divided by the second derivative. And now I can take this difference of optical paths, optical lengths, as 1/3. This L third power of x naught. And then I have this thing power 3, which is this thing power 3/2. So I have 2 power 3/2. I have gamma naught minus gamma power 3/2. And I have this gamma double prime of x naught power 3/2. That's what we need. I will now erase this. And I think I will also erase that. And now we just say fine. So that's the difference between these optical lengths in terms of the deviation from gamma naught. And now let's call it delta L. And we know that when this difference, we just know it from optics, when this difference is an integer of the wavelength, then we have the constructive interference. Then we have the intensity goes up. Now in my notes I use the notation n, which is not a good idea because then it gets confused with the diffraction index. So please take care when you are going to read the notes on the table. So here I'm using m, which is just an integer. Right, and then I can just use this condition and I can find what are the positions of those maxima, which maxima of intensity, which are exactly supernumerary both. I just say that this is equal to m lambda, and that gives me gamma naught minus gamma, minus gamma power 3/2 equals to m lambda, and then this number 3, 2 to 3/2. This derivative, no, sorry, derivative goes to the denominator. and I have this derivative upstairs. Unless I screwed up something, then I can just write that gamma, I will, instead of writing a new formula, I will just correct this one. So gamma naught minus gamma is m to the power 3/2, lambda to the power 3/2, 3/2, and this disappears, and this becomes, oh sorry, 2/3, 2/3, 2/3 here, 2/3, this is fine, and this is 2/3. And these are the positions of supernumerary balls. And what is important is that they go as this integer power 3/3. So if we are thinking about this picture of being a primary rainbow, then here we start having rainbows, and the m 2/3 is, distance becomes less and less. So let me exaggerate a little bit, but it would be like that. So we will have first supernumerary bow, second supernumerary bow, third and fourth, and so on. Of course, in practice, you never see 4, because you really have to have very clean air, which we don't have. But that's how they should be. Now the last part which I'm going to do, and for this I will erase all of that. I think I will only need this. No, I actually need that. I don't even need this. The next part, we are going to get this picture quantitatively and estimate the intensity of those bows. Remember, so we have done it for the Descartes rainbow, and we concluded that the intensity is 0 above the rainbow, and it smoothly goes down below. Now we already see that it would not be correct, but let's do the calculation and estimate the intensity. I think I will also need I also don't need this. I will just need that this equals to delta L. Okay, now to do that, the easiest way to approach, of course, I didn't use these words, but for you, probably the easiest way to do it is to use WKB approximation, which you know from quantum mechanics. Of course, I didn't know quantum mechanics, but that's something which can be used in optics. Now let me remind you what this WKB means. Well, WKB means an abbreviation for Wenzel, Kramers, and Brillouin. And this is a semi-classical approximation in quantum mechanics. You can use it as the typical scale L or R is much bigger than the wavelength. And that's exactly the limit we are going to use this approximation. We will assume that the size of this droplet R is much bigger than the wavelength, which if for light, for visible light, is a perfectly reasonable assumption, because the wavelength of light is, for red light, is 535 nanometers, and droplets are macroscopic, so they are maybe millimeter or sub-millimeter size. So this approximation definitely works for real rainbow picture. Now, in this WKB, what you have done, you could write the wave function or the amplitude of the field, and in quantum mechanics, what you wrote was that this psi was, let me even write, equal c over square root of the momentum, and here we had minus s, and s was action. In quantum mechanics, it's just 1 over h bar square root of no, sorry, integral of p dx, absolute value actually, and it's p over h by is k, so I can write it as k dx, and then it's dimensionless as it should be. No, sorry, it's not exponential, sorry, that's cosine. And this k, again, in quantum mechanics is 1 over h bar square root of 2me minus the potential energy. So you just take that, it depends on the position, and in one dimension it's simple, you just calculate it over x, and then you go and use it as the wave function. If it's not one dimension, it's more complicated, but it's not important for us to do. Now what is important is how do we can write exactly the same thing in optics. And we know that maxima, sorry, we know that resonances must correspond to the zero of this action. So the only thing we need to do is to write the action as just 2 pi delta L over lambda. And then we know that the zeros correspond to this delta L over lambda being an integer, and the action, so the cosine of 2 pi times an integer gives you 0. So that's our action. So it's actually written here. I can write it as S equals to 2 pi times this divided by lambda. But now if you know the action, you can also write, well, in quantum mechanics, the Schrödinger equation, and here we are going to write the wave equation for the amplitude. And how you do it, you just say, okay, let's see what I need. I think this I don't need. And this I don't need. And actually also this I don't. What you are doing, so okay, your equation, well, in our case the variable is gamma, but we can of course also write it for any other variable. For the amplitude, is just k squared times a. Alright, and k is just ds over d gamma. Now, if you look at it, it's exactly the same as Schrödinger equation. Now, I have already erased that, but we have k, which was 1 over h bar square root of 2m e minus u, and then you can you will see that this is actually the derivative of action over x. And then if you plug it in, your Schrödinger equation exactly has this form with this energy and free energy, sorry, energy and potential energy and kinetic energy. Okay, so that's the last part of our story. Let's now take this action and see what equation does it give. And I'm not going to take into account all those terms because what is important for me now is this gamma naught minus gamma of our 3/2. So k is ds over d gamma. So let me call this let's see, how do I want to call it? I want to call it 2/3 k naught gamma naught minus gamma 3/2. And k naught would contain all of that, would contain this and this and this. It's just definition of k naught if you want. Now if I take the derivative, I get 2/3 which cancels, 3/2 which cancels with my 2/3. So I am at k naught, actually minus gamma naught minus gamma power 1/2. And if I get into my equation, I get the second derivative equals 2k naught squared gamma naught minus gamma absolute value times a. And this is the Airy equation. That's exactly the equation Airy introduced when he was solving this problem of the Airy rainbow. And that's unlikely that you have seen the equation in this context, but you might have seen it in your course of quantum mechanics. Because in quantum mechanics, you also get an equation, the Schrödinger equation, which has this form. And this would mean that you have potential which is linear. So you just have potential u of x, which is just a linear function. Okay, here it's offset, so it will be like that. And that's a very common situation. I mean, typically people want to describe, for instance, confined system with the potential which is infinite here, and then linearly grows here, that so-called triangular well. It was very popular for as a toy model for confining potential, because usually the first thing you would do would be just, if you want to confine electrons in nanostructures or whatever, the first thing you would do, you would use the infinite square well, but then there are some issues with the infinite square well, so you typically have a better, you want to have a better approximation, and then you use this triangular well, and the behavior of electrons in triangular well is described by the Airy equation. Now, the Airy equation is not something we can solve analytically, so the solution is called the Airy function. And let me just... So if you have a solution of this equation, y double prime minus zy equals 0, then the solution of this equation is called the Airy function. It cannot be expressed in terms of elementary functions, but it can be written as an integral, for example. It would not help you too much, but I will write it anyway. So it's 1 over square root of pi, integral from 0 to infinity, cosine of uz plus u cube over 3 du. And from this integral, you can derive certain properties. And what we actually need are the asymptotic behavior of the Airy function. Asymptotic behavior. And I will just write it here. So if I have very large argument, then I have something like 2z1/2 e minus 2/3 z 3/2. So that's a super exponential behavior. goes faster, it decays faster than the exponent. I mean, it is the exponent, but faster than e to the power minus z. Now, if we have negative argument, but also very large, then we have an oscillating solution. Plus pi over 4 for whatever reason. And this oscillates. And now, if we apply this, I'm going to draw, if we apply this to this equation, which I already half erased, we can estimate the intensity of the airy rainbow as a function of gamma. So remember, for the Descartes rainbow, we had a singularity at gamma naught. And here the intensity was 0, and here it was decreasing. So that's Descartes. Now for the airy rainbow, first of all, from here we see that we have exponential decay. So we don't have a singularity. So yeah, let me maybe take the Descartes with the dashed line. So for airy, we have finite value of the intensity at this angle gamma naught. Here we have very quick exponential decay. So it's not completely dark, but it decays very quickly, it becomes dark. And here we have, in this direction, we have this oscillating behavior. So we have sine, but the sine is modulated. First of all, the argument of sine is z to the power 3/2, and that's what I already mentioned. So the maxima become closer and closer. And second, we have also the sine modulated with this 1 over square root. So the intensity also decays. It doesn't decay very quickly, like this exponential, but still we have something like that. And this is the airy rainbow. I'm sorry, I didn't mean to say that it's above the Descartes one, so let's draw the two lines on top of each other. And in terms of the rainbow, it means here it's almost dark, so we have a little bit of light and then it becomes dark. And here we have the supernumerary bows, which again become closer and closer to each other. And this is the picture which we wanted to get. Okay, thank you for your listening, and this material is helpful on Brightspace, and then also on Brightspace you will find the materials for the tail, which are my notes which I followed, and also the original tail. Thank you.